Today we're going to talk about time series regression. So this will tie into what we're going to talk about next week, which is clustering, and harken back to when we talked about the processing pipeline earlier. So all the things that we're going to do today are going to apply to ways that you can analyze in SPM and FSL, but we're going to be focusing almost solely on how you do standard timeline regression in AFNI. This can all be operated from the AFNI ProcPy, but we're going to focus on the 3D deconvolve and the nuances of that for what we're going to do today. So looking back at the pipeline processing that would have occurred up until this point, you get all the way through to that scaling, which is right here at PBO5 in this case. All of the PB files are processed bricks, walking sequentially through the blocks which have been assigned. There is also going to be a number of other files and output files for review and for further data analysis, and there's also going to be a couple things that are executables to help you with your QA, which we covered a couple weeks ago. So, just to get people's mind in the zone of what we're talking about a four-dimensional matrix when we talk about the functional time series. Four dimensionals with the x, the y, and the z dimensions, and also the time dimension. Here we've isolated a single voxel, so we've held the x, y, and z static, and we're looking at the voxel time series from a data file. I pulled out the post-Voldredge one, but every voxel will have this continuation of a time series. So what our goal is in regression will be to take that time series through any one of these standard pipelines, including SPM, and reduce that down to a beta weight that describes how much a given stimulus is influencing that. So the way in which that's standardly done is through a linear regression. You can do nonlinear regression, and different packages have different options on how that is applied. But what you'll be doing is you'll be putting in either extracting out earlier or putting into the regression different kinds of regressors of non-interest along with your stimulus regressor to pick up on the signal that you're most interested in. Here we have an example of a two-run task, and we have the three basic blocks of regressors. Two of them are going to be nuisance regressors, the detrending polynomial ones, and the motion regressors here. And the rest are going to be our stimulus files, and those are going to not be provided by the program or from the data itself, but they're going to be given as known external stimulus that will be influencing brain behavior. And we're going to try and isolate beta weights here that will say how much a given stimulus is influencing the signal in a given voxel. So that means for each of these voxels, we will do a linear regression where we'll assign a beta weight to each of the items in the polynomial, each of the items in the stimulus, and all the way through to get and adding in a residual that explains the final aspect of that in this linear regression. That will give us a value for B1, B2, B3 for each of the stimuluses we provide in the polynomial, stim, and motion. And those can create heat matrices. We're also going to get an error time series. and we'll talk more about that one later. So we've now reduced down this whole series of time to our best guess, best fit on what our stimulus files and the other regressors are explaining. Now, there's some things that can throw this off, and there's things that can throw off the calculations. We talked about the polynomial, which was the detrending, and these lower two here. We also have our motion regressors, which are one of the best things at taking out noise, but we also have to be considerate of censoring. Now, our detrends, our polynomials are going to be good for heating, cooling, and things that have sort of a very low linear or quadratic trend. We're going to be good for taking out baseline signal. For taking out a lot of our noise is going to come from head movements. And that head movements can come in various different kinds. There's the sort of slow shifting of the head. There is very sharp jarring jumps in the head. And there's ones where your head shifts and moves to a new position. So we can consider um, the effects that you'll have on the motion will have on the signal, both the abrupt motion and the actual shift of motion. So an abrupt motion, you're not just going to have the effect of moving to a new voxel and any interpolation ensued and any other distortions, but you're also going to be crossing across the gradients. So the signal that comes in is going to be echoed out, and the faster that is, the more dramatic that shift can be, and that can give you very strong slice artifacts. Those really large abrupt head movements, you're going to want to probably censor those out, especially if you're talking about resting state where you have something that's implicating connecting two areas of the brain. If you don't properly take out the effects of motion and censor out the extreme points, you're going to get a very large false correlation of similar noise in similar areas. So there's two ways in which you can select outliers. Here's um, in the first row up here, we have using 3DT outcount. And we talked about 3DT outcount a little bit when we were talking about QA aspects, but the 3DT outcount will give you things that are outside of your mean deviation and um, to the specifications that you can alter through the program. We are masking it and we're taking a fraction of that. We're taking out the trends and we're working out what our outlier count is. And then we're taking out where there's more than 0.1% of the brain is considered an outlier, and that's an indication that you've got too much noise to really want to try to interpolate, and you're taking out that subbrick. Similarly with motion, you can use the frame-wise displacement and you can set a threshold there. Common thresholds for resting state might be 0.2. Some people for other data go as high as 0.5. Here we've set it at 0.3 frame-wise displacement of how many millimeters we are willing for the data to shift before we start considering censoring that out. And once you've cut those out, you still want to put in regressors to take out the noise that will be inherent in the data. So we have taking out, demeaning the motion and taking the derivative out of the motion. The demeaned method just takes out the baseline so we don't get an interaction with that first polynomial. It's not going to have a huge effect. It's a regressor of non-interest, but the derivative is quite relevant because the derivative will get the more abrupt shifts in movement. It will get the when not just this shift in distance, but because it's the first derivative, it will get the velocity, and so it will get things. It will particularly mark when things are in motion, which is where you'll get crossing across the gradient coil. So here's a few little questions for people to ponder out on which things are good controlled regressors, good control moves for different kinds of noise. So major head movement, we're going to get a lot out of the censoring, and we're going to get some out of a derivative depending. If it's really is a major one, then censoring is going to be our best friend there. When we have a minor head movement, then it's the motion and the derivative are going to give us a bit more pickup. Heating, cooling, things like that is going to come down to that polynomial regressor. And to handle crossing across the gradient coils and the artifact that comes from that, you'll probably want to be just at the censoring. So I want to talk about the two major ways in which you map out the hemodynamic, the way you regress it. One is where you can where you assume a shape of a hemodynamic, and another one is where you try to reconstruct the hemodynamic. So the never convolved ones are listed right here, and we'll be talking about those later. The convolved ones, and here we're talking about ones within these two spans, can create a hemodynamic if you give it a stimulus time. Here the stimulus time on the upper panel is 10 and 60 seconds, and you can see we used a WAV, a block, and an SPM, which is SPM's version of a undershoot hemodynamic, kind of like the WAV is Afni's version of an undershoot hemodynamic, and the block is more like closer to a gamma variate function. So the important difference is there is how it introduces the undershoot and how aggressively that's placed in, and also how quickly it moves to peak. So you can tell they're very similar in what they expect from the hemodynamic, but there are shifting differences in how quickly it goes to peak, how quickly it initiates, but most importantly, how it handles that post-stimulus recovery. So if you want to set it, if you have a fixed stimulus that's always occurring for, let's say, 10 seconds, as is the case in these ones, we can set that stimulus to occur and we expect a rising hemodynamic. If we're in a condition where our stimuluses are of varying length or varying amplitude, that's where we start shifting towards needing to use duration modulation. So the DM block is an example of how we can use the 3D deconvolve to have a varying stimulus time length. When we start doing that, that can apply to any of the different blocks. Just an important note, while you can put in the actual times into the path as a 1D and just list out the times instead of directly giving it a stimulus file for most of these functions. For the DM block, it's better to actually have it reference a text file. In this lower example, I want you to talk about the modifications. These basic ones can be just used with stim time, but if you're going to try and use some of the advanced functions, then there's stim times IM and stim times AM. And stim time IM is independent modulation. So in this example, we have a 5-second stimulus occurring at 10 seconds and a 10-second stimulus occurring at 60 and at 110 seconds. So here, in our independently modulated time series, we have the first one occurring in black as IM1, second one in red as IM2, and the third one in green as IM3. So you can see This one is a bit shorter, it's briefer, it has a sharper peak, it's a shorter time frame, and it in black. Then these two are more symmetrical at IM2 and IM3. They're in different colors because they will come across as different regressor lines. So they will all get individual beta weights. And so they're good if you want to build towards an MVPA. You can first run it through deconvolve, and then you can hand that off to 3DLSs, which has a better fit function for LM, according to a nice paper by Munford. So the stim times AM, we're looking at amplitude modulation. And for for the sake of this, I'm using stim at the AM1 as an example to help people think about it, and AM2 as an example of what people should do. As the AM1 gets a little bit confusing on how you could potentially interpret it, so I'm just noting that it exists. So in this one, we've also multiplied it by different amplitudes. So we have a shift in time, but we also have a amplitude modulation of 1, 2, and 3 for the first, second, and third stimulus. The AM1 is here is at a small height from this one, and it peaks up even higher by the third. When you use AM1, it just makes a hemodynamic scaled to that amplitude. What is lost in this is that you have both the effect of task and the effect of load all in one regressor. So it makes it a little bit hard to talk about and operationalize what exactly you're dealing with. However, with stim times AM2, you get two different regressors. Here, the AM1 and the AM2 in purple and gold. The purple one here you can see is a small regressor, which really just is linked to the time and the task. So you can see it's a small blip on each of those. The gold one will be workload. So while the purple one is a task-based one and is just shifting up, the gold one has all of that baseline taken out of it, and we're only looking at the differential, only looking at the effective load. So you can see the first one has less load, and the next two have incrementally more load, and the regressor therefore is mean to 0. This opportunity gives you this purple one is task, and this gold one becomes load. That way you can dissect what you're doing there. So an example would be if you have a task where you're trying to remember words, and in the first one, you're shown one word on the page, second one, you're shown 2 words on the page, and the third one, you're shown 3 words on the page. If you separate them into different regressors, then you can try and come up with a linear compilation or a general linear test to try and figure out how these different items relate. If you do the AM2, then your load difference can come out in the gold, and your task effect can come out in the purple. AM2, you kind of get 2 in 1, and it'll be a little bit difficult to dissociate what you're getting out of that. So thinking about how we apply these hemodynamics, one important thought of it is that you have some level of temporal summation. It's not 100% true that you can just add them up, but when you have adjacent hemodynamics and they're overlapping, you essentially are bumping up that area under the curve, and you're coming up with somewhat close to the linear overlap of those. This means a couple different things. If you have a fast event related design, then you try and model fit two aspects under this curve and try and dissociate exactly what the implication of each of these features will come out to. And it also means that if you have a stimulus that is on for longer, you will see both that ramping that we saw earlier in the extended time. If it gets to be above 5, 10, above 10 to 15 seconds, then you start getting more of a plateaued effect in your data. So your general linear tests can be used on differentially acquired data, i.e. data acquired in different stimulus regressors, and you can come up with a new subtraction or addition of those to get to your new answer. So how does this actually look in real life, or as close as it to as we're going to get right now? So 3D deconvolve, you have your input is your post-scaled data, and then here I set this to local times so that when I specify things in the time blocks, if I have multiple runs, it'll be based on the beginning of that run. And we have sensor. Our combined sensors are listed right here. That's using both our outlier and motion. We've put in a polort of 4. You can set this to auto, or you can pick out a number. The default auto is based on division of based on the length of your trial. So in here we're doing an amplitude modulation 1 in this case, which ideally you really don't want to be doing these, but this is just for our exemplar. And then we're applying a DM block, and here we're just doing a time modulation, as in this text file we tell it how long these times are occurring for. Here, because we're not changing the amplitude through a multiplier, but only by the distance of time to put it through DM block, we're not getting an amplitude modulation that's going to interfere between task and regressor. So it really won't, in this case, it doesn't really apply. Here we have our stimulus file, and these are taken out from that 1D tool. We'll put in the means for each runs, and we'll put in the deviations for each runs. We also have our GLT here, and here we can, if we've labeled data here, we can address it here in the symbolic description and create new contrast throughout here. Finally, we have a T out. It will by default give us our beta weights, but if we want T stats, F stats, anything else like that, R stats, then we can do FOUT, TOUT, ROUT, etc. We'll also want to collect out our error time series here. Now, error time series is going to be very helpful later on clustering day. And the bucket is where we throw all the different non-base stimulus data that we acquire here, and we throw it into our bucket. So a couple different questions. Now, is the hemodynamic response function consistent across the brain? No, that's one of the reasons why you really picking up on mapping out the hemodynamic can sometimes be very helpful. And dealing with tasks with different levels of data, so different challenges, you have the IM, AM, AM2, and multiple regressors. The AM2 is probably your best friend with this one. Multiple regressors is possible, but the IM is not going to help you. That's going to be more for doing an MVPA or Searchlight or those kinds of processes. And the AM1, really something you probably best avoid. So now talking about the hemodynamic. So if you do want to map out what the hemodynamic looks like across the brain, the tent analysis is a good method. And it's the sort of standard method and the sort of default, probably best way of approaching it. We will look at what some of the other ones give you, but for now we'll stick to largely describing what the tent provides. Here, the tent regressors, if you give it a span of 16 seconds with 5 different spikes, you'll get something that looks like this. Here you can see dark blue, red, green, purple, and light blue come up again each time that stimulus comes up for that span, and those are all in their own regresses. Each of those will be applied a beta weight to get maximal fit to explain your data. So in this case, we put it against trying to explain just a WAV regressor. So the WAV regressor here can be shown in red. It's Cox Special. It's that WAV that we used earlier. And what we're essentially going to do is once we multiply those beta weights, we get a construction like this. Most of the data was picked up in that C3 regressor in this case, and a little bit on that, sorry, C4 regressor, and a little bit on that C3, and you can see it reflected in these beta weights. What you can then do is add all these together, and you get what you get in the blue line. This is what you get when you request that IRESP function, is the sum of your regressor times your beta weights in a reconstructed hemodynamic. Then you can display these hemodynamics, and that gives you a mapping of your wave file. If you do want to start playing with other aspects like spline, poly, sine, and exponential, then you can get better fits if you have a fast event related that is truly forming along a WAV or a GAM hemodynamic. The sine does a nice job of picking that up. But if you're mapping out longer events or ones in which you don't purely know the shape of a hemodynamic, tent is a preferred way. It's going to be the more robust way. Getting into things like spline, where you have some undershoots, can lead to strange oscillations in your data, and it'll look like it's coming on and off. And the poly and the sine may try to really fit you to a pure up-down hemodynamic. So you may want to stick with V10, even though fast event-related blip data, you can get better fits going other ways. So how does this actually work in, again, the real life? Here we have sim time set, and here instead of pointing to a text file, we can just say 1D, and we specify the times in which a stimulus is coming on. We have the onset and offset of this time, so it's a 15-second span with 6 regressors, and we can then map that out onto the data. Each of those will be assigned a beta weight, and we'll receive the beta weights for pane 0 through 5, or i.e. 1 through 6, 6 pane regressor beta weights. And then right here, we specified that we want an IRESP. So this IRESP is that math that we did earlier, multiplying those beta weights by those input regressors to reconstruct the hemodynamic. And we'll also, again, be saving out our error time series, because that's just useful, good stuff. So one thing I wanted to talk about was whitening. So if you have a large, if you're collecting data, you get spatial autocorrelation, so that you will really strongly explain your data with adjacent pieces of data. And if your data is best explained by what happened before, not what you're actually doing to it, then it's probably not very useful data, and you can lead to false positives. So here you can see that we have a shifting time series in black, and under it we've whitened that time series. So this whitening was done with an armor in R, but the general idea is that this shifting time series is showing a positive autocorrelation. So here you can see our autocorrelation with a shift of 1 was 0.6, and it goes down to 0.3, and that's a much higher autocorrelation we want to be dealing with. And so to remove that, we do a lagged 1 arm, and we can then get what is here in red, where that initial autocorrelation is removed. If you can whiten your data beforehand, like through film or feed in FSL, or in R, you can use a whitening function. If you're doing it in AFNI, what you'll do is you'll handle it in REML. And again, this is a question of whether you handle things at a deconvolve time, you handle it before. 3D REML will take the stimulus functions that you give it, but it will also put in a lag feature from into your equation to take out autocorrelation. So after you run 3D deconvolve, you can hand off that matrix and then run a nice little brief script that the script line is brief. The program actually runs a lot slower because it's doing more intensive computations, and you can get a nice error time series, which will have a better fit, a better estimate of your variance, and it will also account for that cross correlation. So as you can see, the whitening has a strong effect on sort of little blips of data and correcting for that. Um, if you have a if you have a long regressor that's taking multiple seconds to come on and off, then, or a block regressor, the whitening's not going to have a huge effect. The armor's not going to have a huge effect. But you have a fast event related. That's where you're really going to show shifts in if you hit one of these spikes. And if you didn't control for it effectively, you can hit false positives. So, a couple food for thought is with false positives are higher in due to temporal autocorrelation. False positives are higher in event related or block. The answer would be in the event related. So you need to definitely make sure that you're doing autocorrelation correction on those event related designs. And then mapping the hemodynamic is better for event related or block designs. And here, the event related will give you a better mapping of the hemodynamic. The block design, because of that overlap, you're not really going to be able to dissociate out the tails of the hemodynamic. So a couple things to think about sort of on the QA side with your model design. If you're doing a regression, you want to evaluate that regression, make sure that it's looking okay. You can do that through here with 3D deconvolve no data, and it will give you your some good information on the quality of your data, but it will also tell you if you've got high pairwise correlations between regresses. So if those are over 0.4 or even over 0.6, then you want to be concerned about if you're over-specifying your model. Another nice way about going about that is through variable inflation factor, and this is a sort of a multi-collinearity concern. So we took an example data here with an overspecified model. So we have our poly and our motion, and here you can see that they have very high variable inflation, way over 2. And that's actually okay with me. The reason why I'm okay with that is that the variable inflation means that you have a poor fit model and the data that you get out there isn't going to be robust, consistent, because it's got too many choices of how it's parsing that out. I don't really care in a large respect if the motion or if a polynomial is inappropriately attributing the beta coefficients among these sides. But I really do care if this starts to, the VIF in here is overinflated. So we zoom in on here on the stimulus, and you can see if we put in all the different things that we could think of putting in there, we do start to get a overlap, and we do start to get significant variable inflation that exceeds 2. If it's over 5, then you've really got a mucky model. If it's over 2, then you should really be concerned and look to see, is this really the kind of task design that you want to be putting into your data? So variable inflation, you can evaluate that based on an LM on your data or in R, and you can sort of develop some code to do that. Um, so again, I've been talking largely broadly about how things are done both in the pipeline and in the regression in the world of AFNI, but FSL is a great package and it has a nice lead through. It uses feet on a first level analysis in running this data. Their GUI will let you walk through the different steps and see the options here, but there's also command line options for running feet. And here, if you do the model wizard or the full setup of a model, you can specify a design matrix that and evaluate that design matrix to see if you're effectively um, picking up the data, and you have same question with a gamma variate function or other functions, and how often that's coming on, and you develop out all your contrasts. So these would be like the GLTs, and these are your base regressors going into the model. So you'll notice that there is an awful lot of similarities in the way all these things are done, but the specific way in which you interact with programs will change. Another thing to think about in regard to your model building, your building of your regressor set, is the default output is a beta weight. That beta weight on scaled data is actually your percent signal change, and that is a default that comes through AFNI. But you can also acquire z-scores. The t-scores is a relative z-score, and the z-scores can sometimes be more robust to scaling issues and different, and it tends to be show less variance across individuals. So consider which way you want to be pulling out the data before you start working with it. And oftentimes I find z-scores are a little bit more helpful to work with than the percent signal change, because sometimes just the quality of signal, raw mean signal in an individual can give you an inflated percent signal change or a differential in percent signal change between individuals to a much larger degree than the z-scores would, which will show more just how the quality of the fit between individuals. I'm not. We talked in the pre-processing briefly about CompCore and retro I-core and how those can be used as controlling signal. Um, and just as a preview for when we start talking more about resting state, ICA is definitely your friend. ICA you can run through melodic um, and I just give an example of GIFT in SPM because it's a really nice model. And what you can do with these independent component analysis is you'll derive, and here in this gift screen, it's a nice example, a time course and a location map that will explain a a large component of your data. So the first component is the largest aspect of a data. Your second component is the next largest aspect of a data. Unlike PCA, they're not going to be orthogonal. And you can see that you get these different time courses occurring across the brain. You can relate these into task-based data, but you can also relate these in resting state data. And you can identify, and here I use the melodic example, they have fixed and aroma, of ways of finding noise in your data based off of spatial or temporal characteristics of your independent components, and then you can remove those explicitly from your data. And that's a method used in CompCore. And that can do a great job of cleaning up your data. But more on that later. A nice article to go through, sort of things to think about in your data processing is the Poldrack paper from 2017. So I want to thank everyone for their time, and we will pick it up next time on clustering.